Okay, good evening. We start a lecture today on natural language processing using deep learning. And we will see how many of the ideas of deep learning sequential models become useful to solve many problems of natural language. Now, first of all, we have to talk about what do you mean by natural language? Why do we use the phrase natural? That's because particularly we as computer science people are familiar with artificial languages, right? Things like Python or C++, or these are all artificial languages that have been created for using on the computer, and those are unambiguous languages. So those were developed so that when we write a statement in any of these languages, there is some preciseness to it. But the way people communicate is with not artificial languages, but with natural languages. So in natural languages, it is far from being unambiguous. It is there's a lot of room here for interpretation of what one is saying, and a lot of it depends on the context in which you're saying something. So natural language is much more complicated to deal with than an artificial language. So that is the difference. This is natural language processing by computer as opposed to artificial language processing by computer. So, and then we talk about how probability plays a central role in natural language. Really, where does probability come into play? So this is something sounds counterintuitive. Is it when we talk? Is it all mathematical? Uh, Probabilities come into play because we are making guesses as to what the interpretation could be. What is the most probable interpretation of that? What is the most probable ambiguous word that has been spoken, that has been typed? What is the meaning of this? So on. So we model all of it precisely by saying we'll assign some probability. We'll learn these probabilities. The machine learning method has to learn these kinds of probabilities. Just like, we have seen deep learning is all about probabilities. Even when we're doing supervised learning classification, we are just saying, well, that's a dog with probability 0.99. It's another animal with a probability 0.1, like that. So it's a probabilistic type of interpretation. Same thing here as to what words mean, and we have some probabilities associated with all of it. So probabilities become central to tasks like in machine translation. I speak a sentence in, let's say, Chinese, and it needs to be translated into English. And so there is so many ways you can translate the Chinese into English. But one version of it may be possible, but another version of it may be more accurate and say, that has a higher probability than this other version, which seems to be too literal in interpretation, and so on. So the role of probability is what we begin with. So by doing this natural language processing in deep learning, we begin with actually what is natural language processing. So we talk about the role of probabilities in natural language, and then we'll talk about what are called n-grams. So a simple approach to handling probabilities was to think about words that occur together, like things like what are called as bigrams and trigrams, that's which words occur together. And so maybe probabilities will be computed based upon, those two words seem to go together, right? So we say higher probability that these two words occur together in language in the training set. So we assign a higher probability. In bigrams, we're only looking at two words at a time. In trigrams, we're looking at three words at a time. And in n-grams, we are looking at a sequence of words at a time, like that. So we first go into probabilities. Next, we talk about n-grams. Next, we talk about going into what are called as embeddings. With these n-grams, we're talking about, which two words go together, right? That is actually working with a symbolic representation of the words. The words, the cat sat on the mat. So these are all word tokens. The cat sat on the mat, right? So these are all symbolic representations. What happens with neural networks and deep learning is that we do away with the symbolic representation and we go into what is called as embedded representations. So we now say the words are no longer words in the original form. We begin by saying, words could be represented as vectors, because all of deep learning is about processing numerically, right? It's all about numerical computation. It's about vectors as input. It's about matrices that multiply these vectors. And then it's about convolution with a kernel. These kinds of operations, all of which requires numerical or number form of everything. Whereas we have here the cat sat on the mat. Where would these become numbers? And we start out by using what's called as a one-hot vector representation, where the becomes a word in a vocabulary of maybe 1,000 words. 1,000 words, by the way, represent about 70 to 80% of the English language is only 1,000 words, such a small number. But if you really want to represent 90% or more, you would have to go to a vocabulary of 10,000. Or if you want to represent all technical words and so on, it could be as high as 200,000 or 250,000 words, talking about all medical terms and everything. So the vocabulary keeps on increasing. But at 1,000 words, even with 1,000 words, we can say, what is the value for the? We'd start out by saying, let's have a one-hot vector. That is, we choose a vector to have 1,000 elements. We're choosing a vocabulary of size 1,000. And then we say the occurs, maybe alphabetically. What are the most common 1,000 words? And then we arrange them alphabetically. And then you say the is maybe the 675th word in among these 1,000 is the word the. Then we say, okay, the vector representation for the is 0, 0, 0, 0, 0, 0 until you come to index 675, which is 1, and then the rest are all 0. So that's a one-hot vector representation of the word the. Similarly, the cat. Okay, cat is another word in this vocabulary that would occur maybe around 200, let's say. And so we say there is a one-hot vector for that. So we have one-hot vectors for all of these words. But these are all humongously large vectors. It can be 1,000 dimension, or it can be 10,000 dimension, or it could be 200,000 dimension. So that is a symbolic representation. And that representation doesn't have any sense of meaning. It does not know anything about the meaning of cat and hat. And so it will say cat is as different from hat as cat is as different from the. So we say the symbolic distance between these words is very small. If I give you a vector of size 2, let's say the vocabulary consists of only 2 words, and 1, 0 is one word, 0, 1 is the other word. Then we ask the question, what is the distance between these 2 words? We say, well, it's a vector difference you want. So you want to, along each dimension, the difference is 1. So it's we take sum of the squared differences, 1 plus 1, take the square root of that. So square root of 2 is the distance between the 2 words. Whereas we want in these words to be converted into some distributed representation, no longer symbolic representation, where we say we would like to represent these by a small vector, which is where a deep learning comes into play. And we say this small vector is going to be the hidden units. We can decide what is the size of the hidden units, right? What is the representation we're going to create? We can say, well, it's going to be 300. So instead of dealing with a one-hot vector input representation for a word, we say, well, can you map it into 1,000 into 300? And that we refer to as an embedded representation. And how do we train this darn thing? You're going to supply these words and you're going to convert them to hidden units. Well, we could say on the other side, which is on the output side, we could train it in the context of something. So we can bring in now meaning, saying the cat, okay, after cat, before cat, the occurs sometimes. So we could have cat, or the hat, and all these kinds of things. So we could have at the input each word, and at the output we'd say list of all the 1,000 words, which words occur together with whatever input you're providing. So we could have a training system like that, which provides these pairs of words and at the input and the output, and use that as a supervised learning to learn the embedded representation. So what basically we would be converting is somehow coming up with an embedding where we have elements that where we have words are now no longer one hot vectors, but 300 dimensional embeddings. And where, interestingly, if the words kind of occur together, they will be near each other in this embedding. And if the words don't occur together, then they will be far apart. So there is some kind of semantics coming into play because we are studying the nature of words occurring together and learning what that is by doing a backprop type of learning of all of this. So that's how you learn an embedding. So our foray here today is to talk about probabilistic representations. Our foray is into n-gram type of representations, and then into embedded representations. And there are a whole bunch of issues that come up after you decide on embedded representations. The kind of embeddings are quite large. The input and output vectors are large. So there is all kinds of huge issues in terms of computation. A lot of deep learning studies we've been doing have all been about computational issues. Why did we come up with backprop? Backprop is a way of doing derivatives in gradient descent, and the complexity of it will be order n cubed in terms of the number of weights, and we reduce it to order n squared with backprop. Similarly, here also we need to worry about computational complexity, given that the space here is extremely sparse and extremely high dimensional. If I say here is a sentence which is 5 words long, and supposing each word can take 1,000 possible values, then I ask the question, how many possible sentences can you construct? Well, if you choose, if any word is possible in any position, then it's going to be 1,000 to the power of 5, right? That's a huge, huge number in terms of the ambient space. So you have 1,000 times 1,000 times 1,000 5 times, right? 1,000 3 times itself is a billion, into 4 times would be a trillion, and into another 1,000, I don't know, is that a quadrillion? Maybe. So you have a quadrillion number of sentences if you have a 5-word sentence using one of 1,000 words, but most of them are nonsensical, right? So it will have all kinds of arrangements of these words which don't mean a thing. Whereas a lot of the cat sat on the mat. Okay, that seems like a valid sentence, and that would be okay. So the ambient space may be so large, a quadrillion, but the legal sentences are all going to be on a very, very small manifold, I suppose. You can think of it like that. So these are some of the issues, and there are computational issues here. What else? Yeah, these are some of the basic things. And then we go on to talk about how natural language processing can take advantage of context and so on, which we did already when we did sequential models. So attention models and so on will come up. Okay, so that is my preamble to this lecture today. All right. So before I begin my slides, are there any questions on this overview of NLP? Okay. All right. So let's begin with. Okay, there we are. I had a bit of a difficulty in opening my file, so I think I got it. Okay. Are you able to see it? Hello?
Yes, Professor.
Okay. All right. Um, These slides repeat what I said. By the way, I taught this deep learning course at the Indian Institute of Science in Bangalore, India, this last spring. So my slides for those lectures, we were already into COVID by the end of the semester, around March, April, May, and some running into June also. So I was giving lectures on the same topics. Some of the earlier topics we covered, I was doing it in a classroom. So my lectures are more comprehensive, what I gave in India. Here we have kind of limited time. So I, for example, have only, 2 lectures on this. I had more time in there. So there are more comprehensive lectures on natural language processing. On my public site, I put both the video we are doing here at UB and as well as the Indian version. The Indian version is more complete. So if you are dedicated to NLP or some of these topics, you may want to look at that also. All right. Okay. All right, so what are the topics again here? First is the overview of what is natural language processing. I gave you a sense of it today already. And after overview, we look at n-gram models. I mentioned what n-gram models are. That is the first approaches to compute probabilities of words. And then neural language models. This is the embedding approach. And then how to deal with high dimensional outputs, because the number of possibilities is very large. Number of sentences can be extremely large. And then there are all kinds of clever things like combining neural language models with n-grams. Can we somehow take, this reminds me of the course next semester of neuro-symbolic computing. The item number 4 is something like that. How do we take neural language models, that is things with deep networks, and then with n-grams. N-grams is a technique from the conventional method of AI. So that's combining the two. And then we look at the topic of neural machine translation. How do we go from, Chinese to English, or attention models? Okay, we've already looked at that briefly in sequential models. How are they used in NLP? So these are the topics. So again, this slide is just repeating what is natural language processing. Computers process unambiguous languages. Example, C++, Python allow unambiguous parsing of programs. So we can parse these. So there is a context-free language. It's a context-free language. So one can write a parser for it to determine what exactly was said in each statement. Naturally occurring human languages, example, English, are ambiguous. They defy formal categorical description. People have been thinking over the last 50 years that maybe natural language is amenable to grammars, right? No longer context-free grammars, but maybe context-sensitive grammars, so on, but no. So you cannot write a grammar for natural language. So they defy formal categorical description. Natural language processing includes applications such as machine translation, of course. Learner reads a sentence in a language and emits a sequence in another. That's what natural machine translation is all about, MT. NLP is based on language models. So natural language processing is necessarily based on language models. And what are they? They define a probability distributions of sequences of words, characters, or bytes of natural language. So the inputs are coming in as a sequence here. It's not like a static picture, but they're on sequences. And we are learning distributions of these. What is the conditional distribution given all these words? So that is the type of calculation we need. Given all these possible sequences, how do we calculate the probability? Let's say machine translation. We have one input in Chinese, and then we have got a possible output in English. And then there is another possible output in English and yet another possible output in English. Well, we want to calculate which is the most probable one. So we need to calculate the probability of each of these sequences. So how do we calculate that probability? So which is why we need to learn about probabilities in NLP. This slide says why to use probability in natural language processing. Natural language is ambiguous because its use is situated in a world context. So each sentence that we speak is within the context. And then also we don't say everything. When we are talking, we say little that is needed to be understood. So we know the context, the teacher knows what the students know, and we say, okay, let's assume that. and we'll just go ahead and talk about things without explaining everything. So that is how natural language is. And the tasks involve reasoning about meaning. So that is another reason to use probability. We want to reason about meaning using world knowledge, not in the source text. And we need quantitative techniques. And so we want to move away from unrealistic categorical assumptions of earlier former linguistic theory. Previously, we used to think that a grammar generates these sentences one after the other. And so those would be categorical assumptions that these come together. And so this is more quantitative, probabilistic. So people use these kinds of words. And models that assign probabilities to sequences of words are called language models or LMs, right? So they assign probabilities to sequences of words. Here is the example of probability in machine translation. Here is the Chinese source sentence. Some of you in the class, I think, would know Chinese. Maybe you can read this Chinese, right? And anyone want to volunteer to read that in Chinese to me? No? Can you read it? You have to turn your microphone on.
他向记者介绍了主要内容。
Great. All right. Thanks for being brave and reading it for me. All right. Well, here is a literal translation of this Chinese sentence. He to reporters introduced main content. If you just literally translate it. That is not a very good translation because it's not very meaningful. Potential rough translations is he introduced reporters to the main contents of the statement. Okay, that makes sense. He introduced reporters to the main contents of the statement, or he briefed to reporters the main contents of the statement. Or the final one, he briefed reporters on the main contents of the statement. There are some minor differences between all of these, but this is probably the most meaningful of all these translations. So we say last one is the most probable phrase. That Chinese that was said here has become the correct. So there is a probability of each of these, and we're saying this is probably, the last one is probably the most probable correct translation. All right. All right. So why to use, I went back. Sequential models for natural language. So natural language is sequential, often regarded as a sequence of words rather than a sequence of characters or bytes. So we can also think of each of these sentences here as characters, O, F, T, E, N, like that. And they are of high dimensionality. What do you mean by that? Total number of words is very large. A vocabulary could be 1,000 words, it could be 10,000 words, or it could be 100,000 words or more. So word-based language models must operate on an extremely high dimensional but sparse discrete space. So if we have 1,000 words in the language, a 5-word sentence will have 1,000 to the power of 5 possibilities, of which only a very few, very, very small percentage, if it makes sense. So in a way, we say that only the legal transitions are very small. It's a sparse discrete space, we say. Several strategies have been developed to make models of such a space efficient, but computationally, both computationally and statistically. So there have come up several methods. What could be those methods? N-gram is one of those ideas, which makes it efficient. The embeddings model, all right, that's the neural language models, are make it even more efficient than n-grams. Language model as distributions. Language models define a probability distributions over tokens in natural language. What's a token? A token is a word or a character or a byte, so typically we think of it as words. It could also be characters. I guess in Chinese, it makes sense to be characters, right? But there are a much larger number, so they're all characters there. Whereas in English, we don't look at the character level, we look at the word level. Earliest successful language models were based on fixed length sequences called n-grams, right? So n-grams was an idea which has been around for a long time. Simplest n-gram models assign probabilities to sentences or sequences of words. Using n-grams, we can assign probabilities like the sentence we saw, that the Chinese translation. Neural network language model, the generic methods. So they can be either generic methods or domain specific methods. So the language models that we can construct, well, they are very general. It's about all of English language. Or we can say, no, this is about medical terminology. So a very generic neural network techniques can be successfully applied to natural language processing, right? And so that is the generic methods. Domain specific methods are to achieve high performance and scale well to large applications. Domain specific strategies become important. All right. So we become very domain specific. To build an efficient model, we must use techniques specialized to sequential data. So it could be very specific. Let's say it's about football, right? American football. So we'd have a very domain specific language, and uh, and if somebody says who's going to win this game, and if you say it's the Bills by 3 touchdowns, right? If we sometimes say something like that, it's very specific to the particular game we're talking about. In another, even in another domain, might not know what do you mean by win by 3 touchdowns. All right, so that's an overview. So let me close this one then. Let's go on. Okay, so we'll now look at this first simple idea, n-gram models, right? You might say, well, isn't that an old method? Yeah, it is an old method, but it is worthwhile to keep it in context. Assuming you're going to be a NLP person, this is something very basic. It's like talking about convolutional neural networks by saying, what is convolution, right? Okay, well, maybe that's a basic mathematical concept, but it's worthwhile to keep it in mind when you go into higher level models, what it is. N-gram models. All right. So we again begin by use of use of probability in natural language processing. Here again, two more examples. First of all, why do we need probability? Is predicting the next word. This is an example from GPT-2, right? This is an old version. Today they're into GPT-3. And that's exactly the sentence. The cat sat on the. Can you predict the next word? Well, the options are floor, bed, couch, ground, table, sofa, edge, chair. Oh, there's no mat here. All right. But look at these. The probabilities are floor is the highest, bed is the second, and couch is the third. And instead of mat, we have a ground here and all this, right? So this is, so you can go to this site, all right? You can go to the Allen Institute and you can, it says this demonstration uses the public parameter OpenAI GPT-2 language model to generate sentences. Enter some initial text and the mode will generate the most likely next word, right? You can click on one of those words to choose it and continue or just keep typing, right? So if you can, and the model will generate the most likely next word as you keep typing. Click the left arrow at the bottom to undo your choice. Built it using Hugging Face's PyTorch, PyTorch pretend BERT library. See the source code on GitHub. Okay, so they're constantly doing this. What's the use of saying cat sat on the mat? Is that silly? Is that useful? Well, can you imagine if it kept on generating sentences for you? So you could even make it generate sentences. So you can even get it started with, some good examples of that. So it's called, fake language, right? You can just type in something that they went to the jungle and it'll start making up words like in the jungle we saw some alligators and so on. It will just keep on predicting these things. So you can generate new text by predicting the next word. It becomes predicting the next sentence and predicting the next paragraph and so on, right? So this is about this involving what is the most likely, so that kind of thing, all right? And or we just saw the English, Chinese to English, which is more probable. All of a sudden, I noticed 3 guys standing on the sidewalk. Same set of words in a different order is nonsensical. On guys, all eye of notice, sidewalk, three, a sudden standing. This is a nonsense here. So we'll say, okay, more probable is this one that seems to make some sense. So which is more probable? The ones that make sense rather than the ones that don't make sense. So probability is essential in tasks with ambiguous input, for speech recognition, for grammatical error correction, for machine translation, and so on. So probability, probability, probability. Okay. Computing the probability. So how do we calculate the probability of a word? Now that we say we can generate text, how do we calculate even for one word? What's the probability of a word? Consider the task of computing probability of W given H. The probability of word W given some history. Oh, H is not hidden. This is history. So we say, supposing the history H is, its water is so transparent that, supposing somebody typed in, its water is so transparent that, we want the probability, maybe the most likely when you say its water is so transparent that the, next word is the, what is the probability of the? Well, then we want to calculate the probability. Probability of the given its water is so transparent that. So how do we calculate this probability? Estimate the probability from frequency counts, C. And this is the probability of the given its water is so transparent that is equal to count C. Its water is so transparent that the divided by count, its water is so transparent that. So that's precisely what we're trying to do here. That is, given the context, its water is so transparent that the, then we are saying what is the word that is the, right? So it's the probability the given its water. So this is, we need the counts. For that to be able to say, well, the is got a high probability, but how do we get that probability? We need to have counts. How often on the on your corpus of text do you have its water is so transparent that the? How often do you get that? Even the web is not big enough to estimate probability from frequency counts. If you say, I'm going to find out how often does the word the occur, even the entire World Wide Web will not be enough to calculate even this simple probability. How often after you say it is the occurs or some other word occurs, not going to be possible. So we're going to need some cleverer methods. That's where the idea of n-gram comes into play. So a better method for probabilities. So we use for this the chain rule of probability. So if you want to calculate the probability of a sequence P of x1 through xn, by simple probability, this is exactly equal to P of x1, probability first getting x1, then P of getting x2 given x1, P of x3 given x1, x2, this symbol means the sequence x1 through x2, all the way of xn given x1 through xn minus 1, right? And we can write this as the product of k equal to 1 through n of p of x k given x1 through xn. So where does this come from? It's called the chain rule of probability. You can exactly show that using Bayes' rule that this sequence can be written like this probability. Now, supposing instead of x's, we had words. We had w1 through n means w1 through wn. This is n words here. Supposing we had n words and we want to calculate the probability of that sequence. This is probability of W1 through N is given by probability of W1, the first word, probability of the second word given the first, probability of the third word given the first two, and probability of the last word given all the previous ones. One through that, right? 1 through N minus 1. So we can write this as a product symbol like that. It shows the link between computing joint probability, this is called the joint probability of a sequence, and computing the conditional probabilities of a word given previous words. These are all, this is the marginal of the word. How often does that word occur? This is given that word has occurred. So this is called a conditional probability. So the joint probability becomes a product of the conditional probabilities. So it says if you want a probability of any sequence, you would need all these joint probabilities, conditional probabilities. The intuition of n-gram model is that instead of computing the probability of a word given its entire history, we can approximate the history by just a few words. Because we would need, in order to do this, what is the probability of getting that whole sequence? The same problem we just talked about, the. So that seems like a hopeless task. So what if we just restrict our attention to the last few words rather than all the words? So that is where the idea of bigram or bigrams come into play. Instead of computing the probability of the given, supposing the sentence was Walden Pond's water is so transparent that, right? So what is the probability after this? I don't know if you know about Walden Pond. It's a famous piece of work by Henry David Thoreau, right? He was a he was a writer from New England in the 1800s, and he spent some time near a pond of water, in the wilderness. So anyway, Walden Pond's water is so transparent that, so we can say that's what we want. What's the probability of the? Well, we say forget about all this Walden Pond and water and all that. We approximated with the probability of the given that. The last word was that. Just calculate the probability of. So we now say it's a bigram. So forget about all the past. Just remember what was the previous word. What's the probability getting the? That is not such a bad thing to compute, because we can look through our corpus and say how often does the follow that. Just determine that and use that to say, well, that seems to be quite often, or there might be other words that follow that. So what is the probability? Maybe the is the most likely, and then we say that's the most probably word. We are making the assumption that probability of wn, the nth word, given w1 through n minus 1, given all the previous words, is exactly equal to probability of wn given wn minus 1, and n minus 1 was that. N is the. So this is the idea of bigram probabilities, where we are approximating it by just using two words at a time. Well, we can also we can have common n-grams, count how many times each possible n-gram occurs in the training set. Models based on n-grams have been core building blocks of NLP. So people have gone and computed all these things, probabilities of words, and computed unigrams. What's the probability of x1? The marginal probability of x1 is called a unigram. Every word we say the and cat and hat, we say how often does it occur in this corpus, and we calculate a probability for that. When we say pairs of words, bigram, x1, x2, and n equal to 3, a trigram would be x1, 3 at a time, and so on. So using this idea, n-gram models, an n-gram model, n-gram is a sequence of tokens, example words. N-gram models define the conditional probability of the nth token given the previous n minus 1 token. Now we are allowing to predict based on not just one, but maybe two or three or maybe n. So products of conditional distributions define probability distributions of longer sequences. It says, supposing I want to calculate the probability of x1 through x tau. This says if you're using n-gram, then it says, well, here is p x1 through xn minus 1. You need that joint probability. So it's depending upon a piece of n out of there, n minus 1 that is. And then a product of xt, t equal to 1 n through tau, we go to the end of this tau. So the nth one xt given xt minus n plus 1 all the way to x tau minus 1. So it is saying what is the probability of the next one given all the previous ones there. So this is a conditional probability. It's a sequence of length n, that's what's being given here. And so how did you get this equation? It comes from the chain rule of probability, that probability of x1 through xn, if I have n of these in this sequence, can be written as xn through xn minus 1 times p of x1 through xn minus. You see, this formula can be easily justified because it comes from the product rule of probability. Joint is equal to conditional times marginal. That's all it is. So specifically for bigrams, supposing we say, give me the probability of x1, x2, x3, x4, 4 words. I'm going to use only bigrams. Then it says, well, with bigrams, we also still need unigrams, p of x1, x2 given x1, and then x3 given x2. So these are words occurring together now, looking two at a time. x3 given x2, x4 given x3. Note that these two together, first two, is exactly equal to x1 comma x2 probability. So that could be in the bigram. And all conditionals can be obtained from joints. So that's another relationship you got to keep in mind. When you have a probability for a pair of words, you can always calculate the conditional from the pair. For trigrams, P1, X2, X3, X4 is equal to X1, X2. We're simply applying this formula to n equal to 2 here and n equal to 3 over here. All right, so that's what's happening here. All right, for a 4-word sequence. So distribution of P of X1 through Xn minus 1 may be defined by a different model with a smaller value of n. All right, so we can go about calculating probability of any sequence as long as we have either unigrams or bigrams or trigrams, what have you. If you have calculated all of them, I can tell you the probability of any given sequence. Examples of n-grams. So your tables that you store may look like this: 4 gram. First terms are your house is, last term is great, frequency 19. Your house looks, last term dirty. All right, its frequency is 3, like that. So these are all combinations. How often do these 4 words occur? When the first 3 words are this, and what is the last? This is a conditional probability. How often does great occur, dirty occur, and that kind of thing. All right, maybe it can be conditional, or it can be joint as well. Maybe this looks like joint here. All right, these 4 words at a time, or it could be these 3 given this. All right, those are related to each other. 3 gram would be first terms, house looks clean. Okay, this one is more like a conditional probability here. This is house looks clean, dark, dirty, haunting, lovely, nice, peaceful, unclean. Okay, so we are calculating the probability. This is the frequency. How often do they occur? It's the count. Probability you'll have to divide by the total number of all of these. How many did you have here? Divide by that. Or you have to add all of these, right? And divide by that to make it a probability. Okay. So examples of it, these are all examples of n-grams. Protein sequencing, DNA sequencing, that also uses these predicting the probabilities. That's interesting, isn't it? They're talking so much about DNA sequencing with COVID vaccines today, right? There's something called mRNA, which is going to be the cure for COVID. And there are so many people talking about, what is this mRNA? Is it something you do in the lab? You mix around some things. No, 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 it's not. It's computer code. So this COVID vaccine is coming out of computer code, and say it is all about DNA sequencing and so on. Not quite DNA. They don't manipulate the DNA. They just send you a messenger RNA or something. Anyway, whatever it is. So this is an interesting table. It says, what is the field you are interested in? Like protein sequencing, DNA sequencing, computational linguistics, or computational linguistics. And they talk about amino acids in protein sequencing, in DNA sequencing. They talk about base pairs, computational linguistics. They talk about character level n-grams, or computational linguistics, word level n-grams. So there are some interesting examples here. Protein sequences don't look very interesting to us because we don't know what is a cis and gly and lu and ser and trip. Maybe DNA sequence is easier to understand. Base pair. We know that DNA sequences are things like A, G, C, T, T, C, G, A. It's a sample sequence. 1 gram unigrams would be the probabilities of A, G, C. We just have all these probabilities. We multiply them together. 2 grams will have A, G, G, C, C, T, 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 like that, if for the same sequence. And then 3 gram will say that is a combination of AGC, GCT, TC, so on. Those are triples. For example, in computational linguistics, characters, to be or not to be, sample sequence here. This is the spaces between the words. 1 gram is a unigram, which is only looking at letters at a time. It's calculating the probability of T, O, blank, B, E, like that. Whereas with bigrams, we have 2, O followed by blank, there's a B and that kind of thing. So these are bigrams. And these are trigrams, which are 3 at a time, which have things like BE blank, E blank, O, there's NOT here, so on. And then if you're at the word level, to be or not to be, it becomes unigrams will be each word separately. How often does to occur? How often does be occur? These would be unigrams. And bigrams would be to be or not, not to be, like that, two words at a time. Trigrams would be to be or be or not to, or not to be, right? So these are the ideas of n-grams, how one can have these basic unigram or 3 gram, 4 gram, all of them computed from a corpus. So that can be used to calculate the probability of any sequence. Unigram and bigram probabilities. Unigram counts. I want to eat Chinese food, lunch spent. This is unigram counts. How often do these occur? I want to eat Chinese food, lunch spent. Bigram counts are how often do you get after I want or I, associated with food, I suppose, here, right? And like that. So the diagonals are not interesting, but I want is most often, right? I want. And after I guess this is the first one, this is the second one. I want. Want to is again quite high, right? Like that. So those are the frequencies. These are the counts. How often do you have 827 times, 668 times? And these are bigram probabilities. Those counts have all been converted into probabilities, which are values between 0 and 1. And probability here, 0.33 is very high over here, 0.33. 0.66 is quite high here. Want and 2, right? So on. Anyway, so if you want a probability, let's say you said probability of is not even this sentence. I want English food. So it becomes I given space, probability want given I, English given want, food given English, and space given food. Those are all available in these kinds of tables here. And we use all these, multiply them and say, okay, the probability of that sentence, I want English food, is this probability. So given unigrams, bigrams, trigrams, and so on, you can calculate probabilities. How do we train these n-gram models? We usually train both an n-gram model and an n-1 gram model, making it easy to compute. So if you want a probability of xt given some n sequence here, right? Sequence of size n here, then that probability by the rule of conditional probability is going to be the conditioning t minus 1, this part here, conditioning probability of that divided by probability of the entire sequence, or t minus n plus 1 through t. Okay, that is uh, n-gram probability, that is this sequence of n occurring, and this is a sequence of n minus 1 occurring. That's what this probability is. This is n minus 1, and that is n. So this is how often does that sequence occur, how often does this sequence with one more word occur. Ratio of the two is the conditional probability. So that's the standard relationship between a joint probability and conditional probability. Simply by looking up two stored probabilities can compute this condition for you. For this to exactly reproduce inference in Pn, we must omit the final character from each sequence. All right. So training of n-gram models would be to calculate all these sequences, store them, bigrams, trigrams, so on, and then you can calculate the conditional using two of these, n minus 1 and n. This gives you a more specific example of trigram model computation, how to compute the probability of the dog ran away. What's the probability of this? It says the first words of the sentence cannot be handled by the default formula on conditional probability because there's no context. Instead, we must use the marginal probability of the words at the start of the sentence. We thus evaluate P3, they're using trigrams here, P3 of the dog ran. The last word may be predicted using the typical case, away given dog ran. Right? Putting this together, the probability of the dog ran away is equal to P2 of dog ran, and then P3 of the dog ran and P3 of dog ran away. See, it's the probability of the dog ran away here. That's what it's calculating here. Okay, so this comes from the previous formulas. All right, so a limitation of maximum likelihood for n-gram models. Pn estimated from training samples is very likely to be 0 in many cases, even though the tuple may appear in test set. All right, so this says, well, it sounds great, but a lot of them are going to have zero probabilities, right? When Pn minus is zero, the ratio is undefined. Okay, to avoid such catastrophic outcomes, n-gram models employ smoothing. So n-grams are not free of trouble because many of the sequences you're interested in is all not occurring at all. So that's zero. Smoothing techniques is add non-zero mass to next symbol values, or mixture of higher lower order n-gram models, or back off methods. Look up lower order n-grams if frequency is too small. So there are all these clever techniques. And there's something called n-gram with back off, and it defines these n-gram probabilities in some way. Back off coefficients alpha and p come into play. All right, so there is more to this. And so anyway, in spite of all of the shortcomings of n-gram models, they're vulnerable to cursive dimensionality. There are if V is the size of the vocabulary, and so the number of possible n-grams also can be large. If you're using 2 grams, vocabulary is already 1,000, we're saying, or maybe 10,000. And then n-gram is 2, that's already 10,000 times 10,000, right? So that's going to be, 100 million already, right? The number of n-grams you need, even with n equal to 2, let alone if you use a trigram, that's going to be already running into billions there, number of n-grams you need. Even with a massive training set, most n-grams will not occur. If you're saying I need 1 billion n-grams, how big your training set should be, right? How massive? If you need a billion of these, then you have to have trillions of words and so on, or larger. One way to view a classical n-gram model is that it is performing nearest neighbor lookup. In other words, it can be viewed as a local non-parametric predictor, similar to k nearest neighbor, and any two words are at same distance from each other. That's another point. Any two words are same distance. I already mentioned to you that what is the distance between two words in this one-hot representation, and they would all be like square root of 2 for every pair of words. Anyway, class-based language models. To improve statistical efficiency of n-gram models, introduce the notion of word categories. Share statistics of words in same categories. Or we can use a clustering algorithm to partition words into clusters based on their co-occurrence frequencies, so on. So still much information is lost. So these ideas have been used with n-grams. So that's what we have to say about n-grams. We have to go on now to embedded models. This is not about just n-grams, and we just wanted to um, introduce that topic. Okay, so we're going to go now to the next topic in our sequence. By the way, we are in chapter 12.4 of our study of deep learning. Okay, we are in applications, NLP, and we finished 12.4.0 and 12.4.1. Let's go to 12.4.2, which are called neural models. Okay, we are into deep learning now. All right, the topic now is not simply language models, but neural language models. Okay, neural language models is nothing but deep learning used for language modeling. All right, so what are the topics in neural language models? One is word embedding as distributed representation. So you see, one of the key things about neural networks and deep learning is that the representation we use is not symbolic, but it is distributed, right? So, and then we'll talk about visualizing word embeddings using TSNE. Maybe some of you have used this method. How do you display multidimensional spaces in 2 dimensions? It's nice to see what do they look like. So TSNE is a way of mapping into visualizing multidimensional data. Then we talk about word-to-vec training. So we're saying this is about going from words, from one hot representation to the embedded vector. We call it as word-to-vec. And then there are subword models. And then GLOVE is an unsupervised learning of embeddings, power of embedding. So these are the topics here. First of all, once again, reinforcing to you what is meant by distributed representation, all right? So we extract n binary features. These are like hidden units. That's exactly what a neural network does. We extract n binary features. A hidden unit divides RD, d-dimensional space, into a pair of half spaces. We are using binary features, right? With n units, the number of regions distinguished is of the order of n to the d. And with order nd parameters, we can represent order nd regions. There's quite a few regions in space. We can get 3 squared equal to 9 regions with 3 times 2 equal to 6 parameters. This is illustrating this point that by using, this is all h, you see, h equal to, there are 3 hidden units. In this case, this original space is 2-dimensional. And we are using here 3 binary features. And the hidden unit vector is h1, h2, h, the 3 values. They can only be 0 or 1. By specifying 0 or 1 with these 3 bits, we can get 2 to the power 3. We can get 8 possible values, right? And so this is showing the regions that are possible separating of this space when h 110 here, 100 here, 101 here, and so on. And then there are boundaries between each of these. And so this space corresponds to only this and so on. So you can get a partitioning of the space based on this distributed representation. That's precisely what a neural network does. It's as if we went into 3 hidden units. That gives you how many divisions of the space would be these boundaries that we draw. They correspond to what? This is H1. One side is positive, the other side negative. This is H1 here. This is H2 here. This is H3 here. One side is 1, the other side is 0. That's what it is. So that's how H's define the regions, because the H says is either 1 or 0. One side is 0, the other side is 1. Okay. In the symbolic representation for order nd regions, if you wanted n to the power of d regions, we'd need order n to the power of d examples. So you would say if you want 3 regions, we have 3 samples which are dividing the space. This is if we directly went into a standard representation. For 3 squared equal to 9 regions, we need 9 samples. You're saying if I wanted this many regions, you'd have to give me 9 samples. Here we are able to achieve it with a number of parameters equal to 6 parameters were needed for specifying this. So the number of parameters would be like how many samples you need if you're using a nearest neighbor type of representation. And so the number of samples, the number of parameters goes up, number of samples needed goes up. All right. So if you're using a one hot representation, the representation would require an extremely large number of for all separate representation for each word, right? Here with the distributed representation, there's all kinds of sharing going on. Fewer parameters mean fewer samples needed. One hot vector is symbolic. Right? It's only this region, it's only this region, it's only this region. Embedded representation is distributed. It is of this nature. So that is the essence of storing raw words versus storing a vector representation, which is an embedding. How do you learn these embeddings? Learning embeddings? Starting with words in one hot vector space whose dimensionality is vocabulary size, say 10,000. Each word is a distance square root of 2 from every other word. Example, vocabulary of size 2, distance between 0 and 10 is equal to square root of 1 plus 1, that's equal to square root of 2. Instead of the symbolic representation, we embed them in a space of lower dimension. Instead of 10,000, can we map into 300? where words appearing in the same context are near. So we have here input a 10,000 element vector where only one of them is turned on, that corresponds to one word. And you have, let's say these are 300 hidden units over here. So these are 300, yeah, exactly 300 nodes here. So what do we connect on the other side? The other side is a softmax layer going to all the vocabulary. A for ant and all the way aardvark, barber, going on to Z for zoo. There are 10,000 words over here. So how are we training it? We just put in a word, the, and then it's cat. Cat is one over here. We say, okay, we train it saying the cat, it occurs together. So the occurs together, that'd be one. And then of course, with other samples, we might say the hat and so on. So it's going to learn what is the association between each word and each of these words. It is figuring out a representation of only 300 elements, which is capturing in some sense which words go together, which is essentially a representation of meaning actually. So that's the beauty of this thing, of going into an embedded representation, which captures things that are similar nearby. And we're using some method of how often, this is called as a proxy. So what we're doing is some kind of a proxy is being used to do the training. So it need not be two words occurring together. There are other clever methods of doing it. So word embedding values. A word embedding, W, maps words to numbers in n-dimensional space, or n. Word W is mapped into a vector of n equal to 200 to 300 dimensions. Like, for example, the word embedding W of cat becomes 0.2 minus 0.4, 0.7, or the word embedding for mat becomes 0.0, 0.6, minus 0.1, all right? Typically, a word embedding is a lookup table parameterized by a matrix theta with a row for each word. So we'd say the word embedding with these parameters for the nth word is parameterized by matrix theta. So there is a nth row of that matrix, all right? So that would be the word embedding. So we can kind of extend this to phrases, one hot vector to embedded representation, one hot vector inputs ride and a, and we're using word to vec representation here. And that gets mapped for some neural network for some task. And we say the phrase ride a somehow combined the network for this is one hot for ride, one hot for a, they're somehow being merged together to create it for ride a phrase. What is interesting about it is word embeddings in a machine translation model. And we are zooming in on areas where related words have embeddings nearby, countries, dates. For example, here we are now looking at a two-dimensional representation using a method called TSNE and seeing where do they end up here. Look at that, France, China, Russian, they're all nearby. This is Germany, Iraq, Ontario, Europe, they're all here. Japan is over here, English, French are over here. We never set out to say these are all similar words. They were just looking at some data set and we were mapping it into a 300 dimensional space and then producing it into 2 dimensions over here. And look at that, there are all kinds of similar things are coming together. It's as if it's understood the meaning. It says certain dates are together here. These seem to occur together. And here is another one, visualizing word embeddings. Look at this here. November, September, December, August, July, they're all together here. Saturday, Sunday, Friday, Wednesday, Thursday, Monday, Tuesday, they're all together here. Him and them are here, and Iraq, Israel, Russia, Europe, Britain, France, Germany, Japan, London, China, they're all here. British, Australia, American, European, Russian. It's as if it knows something about geography. No, nothing about geography, right? And domestic, total, local, foreign, national, public, private, they're all. So this is a magic here. We are just taking all these and mapping it into a network which is creating these embeddings, and we are just saying they're occurring in similar ways. You know, the word occurrences are in similar ways. So it's finding representations or the hidden units are coming very close by, and that is what's coming out here. The representation, the 300 dimensional embedding is looking. So the um, resulting map makes intuitive sense, right? So TSNE is just a method for doing this representation. And it says it's called T stands for distributed stochastic neighbor embedding, and T distributed. And TSNE differs from PCA. PCA, if you map all those words from a 300 dimensional space, it might look like this. And it's being mapped into TSNE, which maximizes the separation of these different regions very nicely. It maps them up like that. Otherwise, it might look a more mixed up. So they were using TSNE. And this slide just tells you what is this TSNE. It's a way of mapping from a high dimensional space to a lower dimensional space, just like PCA, but it's meant for better visualization and maximizing the separations. Okay. So neural language models are unlike class-based n-gram models. N-gram models were all based on symbolic representation, what these words are. Here we are forgetting about all the words. We're just saying there is an embedding type of model. Unlike class-based n-gram models, neural language models are able to recognize that two words are similar without losing the ability to encode each word as distinct from others. Yeah, that's another important thing. It doesn't say that January and July are the same word. January and July have slightly different vector representations, but the distance between the two in vector space is small compared to July and, let's say, a name of a country, right? So those would be different, but things that are kind of meaningfully similar come together. Word occurrence, word to vec again, represent noun by co-occurrence with 25 verbs. So they were looking at verbs, semantic feature values, celery, and they were looking at occurrences with verbs like eat, taste, fill, see, clean, open, smell, touch, drive, wear. They're all verbs. And it's saying, oh, okay, eat has a high probability here, eat and celery. And this is not a, this is, I guess in this embedding world, it's giving it a high value here, and others are all low here. They all seem to be adding up to one here, right? It's almost like a probability. Semantic feature value for airplane. What is the verb that you could go with airplane? Ride, see, say, near, open, hear, run, lift, smell, wear, taste, rub. They're all zero here, but ride is high here, right? So these kinds of co-occurrences are being captured. So one could do train it saying just in your text, if you're able to give as input not just neighboring words, but you're saying this noun with a verb. If I'm feeding it like that, you can train it to get these. So strength of neural language models: share statistical strength between one word and its context and other similar word and context. So there is what is being shared: statistical strength between one word and its context and other similar words and their context. Context means the word that's coming similar to it, close to it. Distributed representation allows model to treat words that have features in common similarly. So we're able to treat words that have features in common. These words are similar. Overcomes curse of dimensionality for sequences. So with sequences, you have to maintain the difference between each word, handled by relating each training sentence to an exponential number of similar sentences. This is where the power comes in. So importance of word embeddings. Neural networks in other domains also define embeddings. Well, we know about computer vision. Convolutional neural network, or CNN, provides an image embedding. We saw that. We go into higher level representation to do final recognition. Those are also embeddings. But we're saying embedding in NLP is more interesting since natural language does not originally lie in a real valued vector space. That is what's interesting here, is that with images, we said, well, they're all pixels. Those values are all between 0 to 255 and so on. They're all numbers anyhow. Here is what? We had all words. They're all symbolic, and we are mapping all of that into numbers. So I have some more examples here of word-to-vec training. we have training, proxy task. This is the proxy task. What kind of task? How are we going to train it again? Let's say we had a sentence, the quick brown fox jumps over the lazy dog. Let's say we use this and say we passed a little window over these words and says the the window is on the, and we say what follows the quick. I'll say okay, the quick, and then we move it to the next space is what follows quick brown. Okay, right. So it says the occurs with quick and the. So I say I suppose this is a, we are looking at what follows one and follows after two, so that becomes the and quick. What about next time around? Now we move this over, this blue coloring to quick, and we ask quick occurs, co-occurs with, I suppose, the already here, co-occurs with the, which we saw that already. And then quick brown, and then quick fox. So this is capturing a relationship between these words here in this box. And then now we're saying, move this one to the next one here, and they say, and says brown, the brown, quick, brown fox, brown jumps. That's what these are. Then we move this over to fox, and then we get fox, quick. I suppose this window is of size 5. Okay, so this, in the beginning it was confusing. It was 3 here, 4 here, 5 here. Now that we reach 5, we forget about the. Fox appears with quick, fox appears with brown, fox appears with jumps, and fox appears with over. So now we have training samples, pairwise, the quick, the brown, quick, the quick brown, quick fox, brown, the, etc. So we can use that to do training now, right? The input vector, this is a one hot vector, and we have 300 hidden units here. And then we have these outputs here. What are these outputs? We'd say, well, if you're feeding in here, let's say the, and we would have all the words here. This is a 10,000 word vocabulary here. And we would have everything set to 0 except 1, the quick corresponds to that training pair. The brown would be another training, you know, quick, the quick, so on. So we kind of keep on, for this input, that should be the output like that. And we do, SGD, stochastic gradient descent, and we learn the embedding. So the word to vec is one hot vector mapped to embedded vector of 300. And the word embedding, similar words are close together. And this is again showing a TSNE representation, those kinds of words. There are lots of examples of training to create word to vec, So I gave you a few examples. The words pairwise, or we can do something else. They're near each other, but not pairwise. Or here is another word to vec trainer, W initialized with random vectors for each. So these are the random vectors. Learns vectors to perform some task. Task is tell whether 5 gram is valid or broken. So training data, legal 5 grams. You say cat sat on the mat. And then you have, that's a valid sentence, cat sat on the mat. But make half of them nonsensical by switching with a random word. Cat sat song the mat. That's nonsensical. So we say R of cat sat on the mat equal to 1. R of cat sat song the mat equal to 0. Okay, so we have a value of 1 or 0. And once we now feed this cat sat on the mat, and at the output we say that is legal or that is illegal. And so that is the training, the supervised learning here, that's figuring out now as to what these weights ought to be by this training process. And we need to learn parameters for W and for R, and R is not as interesting as W. So how do you map into 0, 1, right? It becomes a logistic regression over here. But these weights are not as important as these ones here. So entire point of the task is to learn these Ws. Okay, cat is this particular weights here. This is a network going on here. So this is how we're learning the embeddings. So by doing this, just this mechanism of nonsensical strings and legal strings, words closest in the embedding, words with embedding closest in a given word. France is close to Australia, Belgium, Germany, Italy, Greece. All these words are most similar. Embeddings closest in TSNE space or 300-dimensional space. Jesus, God, Sati, Christ, Satan, Kali, Indra, Vishnu, Ananda, Parvati, Grace. It says these are all very similar. We never taught it that these are all kind of symbols of God and things like that. It's kind of learned all that stuff. Or Xbox is like Amiga, PlayStation, MSX, iPod, Sega, Dreamcast. It's learned all this. Reddish is kind of similar to greenish, bluish, pinkish, purplish, brownish, grayish, yellowish. Scratched is like nailed, smashed, punched. Isn't that interesting? So we got all these megabytes is going along with things like baud and bit per second and megabytes per second and octets and things like that. Right. So how was this trained? As the previous slide, it showed legal occurrences and illegal occurrences. That was enough for it to learn all this stuff, that these are closest in that space. The vectors are close together. Power of word embedding. Similar words being close together allows us to generalize from one sentence to a class of similar sentences. Not just word for synonym, but switching a word for a word in similar class. So we're saying wall is blue, wall is red. Allows a general from one sentence to a class. So they were saying this sentence is similar to this sentence. Wall is blue and wall is red. And wall is blue, similar to ceiling is red, all these things. So many meaningful things can happen, which kind of tells you what is behind all these fake news and things like that, how we can generate these things. Word embeddings and analogies. Analogies between words are encoded in different vectors between words. Example, constant male-female difference vector. The word vector for woman minus the word vector for man is similar to word vector for aunt minus word vector for uncle. Word vector for woman and word vector for man, the difference is similar to word vector for queen and word vector for king. Not surprising, since we write she is aunt but he is the uncle. So we say man to woman, the distance between them in vector space is similar to the distance between uncle and aunt, between king and queen, and analogies. It is learning that. Isn't that amazing? All these analogies and things like that. We think we are very smart when we figure out analogies. Say these two things. Okay, it's similar to those two, isn't it? This is figuring it out in such a brute force way, and it's already figured out these things. More sophisticated relationships are encoded. France to Paris, Miami, Florida, Einstein scientists, all this, Sarkozy, France, Berlusconi, Silvio, all these pairwise, more sophisticated relationships are encoded. Italy to Rome, Baltimore to Maryland, all these things. Japan to Tokyo, Dallas to Texas, IBM to McNeely, right? All these things. Example 3. Word embeddings and relationship pairs. All these are side effects. We didn't even set out to do all this. All these properties of W are side effects. We didn't try to have similar words close together. We didn't try to have analogies encoded with difference vectors. All we tried to do was a simple task whether sentence was valid. These properties popped out of optimization process. Neural networks learn better ways to represent data automatically. Is that something? All these things that we think are intelligent are all done at a neural level. There's no symbolic reasoning going at all. Subword models, same architectures for word level models, but use smaller word pieces, letter pairs, characters, right? So these are word pieces or letter pairs, things like these are not like full words, but pieces. Word embeddings can be composed to character embeddings, generates embeddings for unknown words, similar spellings share common embeddings, solves out of vocabulary problem, out of OOVs, out of vocabulary, it's not even in the vocabulary. Character level embeddings outperformed word level embeddings in English to check machine translation. Wow. Why do we have to train by words? Can't we just do train by characters? We just saw what it was earlier on. And we can do all these embeddings together, learn just which pairs go together. And it says for some tasks that seems to be better. And here's a, so they're all variants. There's a basic word embedding, and then there's talking about character level embedding. And then GLOW is global vectors for word representation. Previously, all of it was supervised learning. Now we are doing unsupervised learning to obtain vector representation for words. Training performed on aggregated global word-to-word occurrences statistics from a corpus, and the resulting representation showcase interesting linear substructure in word vector space. So that thing, man to woman, king to queen, and brother to sister are roughly equal. And it can also be done in an unsupervised learning way, where we don't say these two come next to each other and so on. We simply use some kind of an unsupervised learning where global word-to-word co-occurrences. I guess we do still need co-occurrence statistics from a corpus. How often do they occur? And use that to learn another kind of embedding. Importance of word embedding. Neural networks in other domains also define embeddings. Convolutional neural network provides an image embedding. And embedding in NLP is more interesting. We said that already. Using distributed representations also used with PGM hidden variables. PGM is this thing, neural method, symbolic methods, probabilistic graphical model is also used. So how do we use distributed representation with PGM? That's a topic I'm hoping to explore with some of you, whoever is interested in studying papers. Of course, in these kinds of seminars, we end up studying whatever looks most interesting. And I'm thinking, let's just start out with neural symbolic methods like this. How do you combine neural networks with PGM models? So it might take us in some directions. And given the rapidness with which papers are coming out on absolutely different topics, we can explore that. I'm expecting only a small class, maybe about 10 of you, maybe, hopefully. And we'll study some papers and keep up to speed. I don't want to look at things that, I've done these things earlier on with some other topics, but then they come and go, like some topics like capsule networks. All right, we did capsule network. All right, that's become old now. So we go on to the next thing. A generative model. GAN was a big thing. All right, okay, fine. GANs are now, everybody understands GANs. NLP today is a big thing, right? BERT and GPT-3 and all that. So that seems to provide, this is saying these are useful with NLP. So neurosymbolic is largely going to be done with NLP. So if you're going to be interested, this style of machine learning, deep learning with NLP, particularly neurosymbolic, okay, you got the seminar for next semester. Okay, all right, then I'm going to stop here. Mohammed, what do you think?
Yeah, yes, Professor.
You're okay. All right, then. I'm gonna stop today's lecture, and we can chat a little bit more.